Good morning, everybody. This is Missing Moon. The premise of this talk is that it is thought that the impact of a hypothetical planet called Theia collided with a very young Earth 4.5 billion years ago and produced the moon. But the premise of this talk is, what if the impact never happened? What if Theia missed the Earth rather than hitting the Earth 4.5 billion years ago? Would we miss the moon? So it's a sort of, if you like, alternative history of a moonless Earth. And you could ask, well, why does it matter? If it's purely hypothetical, if it's purely conjecture, why does it actually matter? Well, it matters because one of the biggest questions we can ask is, are we alone? Is there life out there somewhere? Just for context, there are something like 20 billion stars similar to our sun. The Milky Way contains hundreds of billions of stars, but about 20 billion are similar to our sun. And if only a relatively small fraction, like 10% of those stars, have Earth-like planets, which is considered a reasonable estimate, that means there are something like 2 billion Earth-like planets going around sun-like stars. As Carl Sagan said, if it's just us, seems like an awful waste of space. So if there are 2 billion Earth-like planets out there, if you assume that an Earth-like planet needs a large moon to ensure that the planet is hospitable to life, for the reasons I'm going to be covering this morning, if you need a large moon, then the probability of life in the galaxy goes down enormously, because we don't think there are that many planets out there with large moons. And large in this context always means large relative to the size of the host planet. So if it turns out that having a planet hospitable to life needs a moon, then we could be alone in the galaxy. If it turns out that you don't need a moon for a planet to be hospitable to life, then the chances of life out there goes up enormously. And in this talk, I'm talking about habitable, meaning possible for life. Hospitable means an environment that's nurturing and good for life. So without the moon, what would be different here on Earth? I've picked out 5, there's probably more, but I've picked out 5 aspects in which life would be different here on Earth. And those are the different aspects. Without a moon, we'd be in a different environment because of tidal forces, because of the tilt of the Earth, because of the magnetic field, because of asteroid impacts, and because of eclipses. And assuming there's enough time at the end and we have a few minutes spare, I'm just going to add at the end, how would things be different if, instead of Theia hitting the Earth, what if it missed the Earth, and what if it hit Venus instead? You might say, well, it can't make any difference whether Venus has a moon or not. It might make a difference whether Earth has a moon, but surely who cares whether another planet has a moon or not? There is a consequence of Venus having a moon like ours. Right, this alternative history talk does contain quite a bit of conjecture. That conjecture is on the whole based on research and simulations and facts, but it's still conjecture. And the conjecture is, in a sense, my opinion, which doesn't necessarily align with the IOP, the university, the Royal Astronomical Society, or indeed anybody else. So if you think it's the rantings of a crazy scientist, well, I don't think so, but you can have your own opinions if you wish. So the moon, of course, has been our companion in Earth's skies for the last 4.5 billion years. We haven't been around that long to watch it, but the moon has been in the skies for 4.5 billion years, a familiar sight since life dragged itself out of the oceans. It is thought that Theia collided with Earth, but where did Theia come from? What was the origin? Well, again, conjecture, we don't really know, but it's thought that maybe Theia was an object at one of the Lagrange points of Earth. This is the standard way of thinking of Lagrange points. This particular diagram has got the moon, and if we're talking about Theia hitting the Earth, of course the moon doesn't exist yet, so let's take the moon out of this, and let's think about those Lagrange points. There are 5 points where an object can exist, in effect, in a parking place relative to the Earth. And it's thought that maybe Theia came from either L4 or L5. In other words, at the same time that the Earth was formed, another object was formed at the same distance from the Sun, perhaps 60 degrees ahead of Earth or 60 degrees behind Earth. And at some point it was perturbed, maybe Jupiter gave it a nudge, and it eventually migrated and collided with the Earth. And this is what we think might have happened. This is a simulation from Durham University carried out relatively recently to try and explain the origin of the Moon. So Theia, an object about 10% the size of the Earth, collided with the Earth. Both were essentially molten at the time, which is why it's behaving the way it is. You can see a lot of material is sloughed off, some of which immediately falls back to the Earth, and some of which seems to produce two blobs. The larger blob is too close to the Earth and falls back and is reabsorbed by the Earth, and the little piece that's left is what we now call the Moon. Seismic waves allow us to tell what's going on inside the Earth. For quite a while now, we've been using earthquakes and seismometers around the world to tell us what the interior structure of the Earth is. And back in the 1980s, some very odd structures called superplumes were found at the boundary between the core, shown here in red, and the mantle, shown here in grey. One of these superplumes is below Africa, and the other one is below the Pacific Ocean. And the question that's been raised by geophysicists is, are these what's left of Theia? The planet hit us, but wasn't completely absorbed. There was still some segregation, and are these bits here what's left of the planet Theia, which has sunk through the mantle, but not been completely absorbed into the iron core of the Earth? Again, that is conjecture. There are alternative ways of explaining these plumes, but it's interesting to think that the planet Theia is actually under our feet. How can the Moon possibly affect the Earth? The Moon's mass is only about 1% of the Earth's. Sometimes we forget how small it is. Yes, it's considered a large moon in the solar system because it's larger relative to its host planet than most other moons of planets, but it's actually only about 1% of the Earth's mass. And here the sizes are shown to scale, but of course not the distance between them. If we want the Earth-Moon distance to be shown to scale, we have to separate those two by quite a large amount. So there, the sizes and the separation are both to scale. And it's a reminder of just how far away the Moon is, which is why it took the Apollo astronauts 3 days to get there. The distance between the Earth and the Moon is equivalent to something like 30 Earth diameters. Or another way of putting it, in between the Earth and the Moon, you could actually fit all the planets of the solar system. I'm not sure how you would do that, but in fact, there's enough space to do that. So let's think about the first aspect in which the Moon affects the Earth, tidal forces. One of the reasons I started writing this talk was because I was getting fed up reading all sorts of rubbish on the internet about the effect of the Moon on the Earth. There are various statements on the web, including, without the Moon, there would be no tides, which is wrong. There's also statements like, without the Moon, the tides would be in during the day and out at night, which is also wrong. And I thought, well, the best way of describing this is with an adjective that starts with a B. And you know what word I'm thinking of? That's right, this is absolute balderdash. So let's think about tides. And I realized, on looking at various internet sources, there's an awful lot of misconceptions about just how tides are generated. I looked at various web pages and various YouTube videos. I found that about 20% of all of the videos I looked at don't actually explain why we have tides, and specifically why we have 2 high tides during the day, 2 high tides and 2 low tides. I found that about 40% of them did explain tides correctly, but I also found 40% of them did not explain tides correctly. And these were sometimes videos produced by physicists. And yes, even physicists sometimes get it wrong. I know that's hard to believe, but yep, and physicists really ought to know better. So perhaps there's no surprise that a lot of people trying to explain tides get it wrong if they're using sources from physicists which they regard as gospel or reliable, and they're wrong as well. So let's have a think about what's actually going on. The bottom line is tides are generated only by gravitational forces. A lot of people incorrectly say that tides are generated by the pull of the moon raising tides on this side, and on the opposite side there's a bulge. Oh, that must be centrifugal forces or something like that. Nope, there are no such thing as centrifugal forces generating tides. Tides are generated by gravity. If we think of the fact that the pull of the moon is larger on the right-hand side because it's closer to the moon, obviously not to scale in this diagram, the pull from the moon is stronger on this side than it is on the other side. If we actually show the forces of gravity relative to the center of the Earth, we see these are the actual forces that are pushing water around. And it is the horizontal component of those forces, regardless of which way the force is actually generated. The moon doesn't pull the water up. If it did, then if it's capable of raising the Pacific Ocean by a few meters, it's certainly capable of raising the water in my mug by the same sort of distance. But no, the moon doesn't pull the water up, it pushes the water sideways. The horizontal component of these various forces result in tides and tidal bulges as shown. So we get a bulge on this side and a bulge on that side just by following the arrows and which way the water is being pushed around. What would happen if we had no moon? Some people say we would have no tides, which is wrong. Without the moon, we would not have lunar tides, that's correct, but we would still have solar tides. The sun generates tides just like the moon does. The size of the moon and the sun in the sky are very similar. That's why we got the eclipse the other week. And therefore, the size of the tides are very similar. In fact, the density of the sun is a little bit lower than the density of the moon, so the solar tides are a little bit smaller than the lunar tides. They're about half the size. So for instance, if the tidal range of the Mersey is about 10 meters or so, without the moon, the tidal range of the Mersey would only be a few meters. We wouldn't need tide tables. At the moment, we need timetables to get used to the idea of the moon goes around the Earth, and so the high tides and low tides are at different times every day. But if there were only solar tides, the high tide would always be around midday, and the low tide would always be around midnight. There are statements on the web such as, without the moon, the Earth's rotation would be really slow. Wrong. This is absolute claptrap. No. If we think about what's actually happening, the interaction between the moon and the Earth, there's the moon raising these tides. The tidal bulges are there, but Earth's rotation, which is of course quite fast compared to the motion of the moon, that carries these tidal bulges a little bit ahead of the moon. That angle there is about 3 degrees, so this isn't quite accurate, but it gives you an idea of what's actually going on. The moon pulls on this closest bulge, which is slightly ahead of it in terms of where it is in the orbit, and that tends to put a brake on the Earth, and it actually pulls the moon along and accelerates the moon, sending it to a higher orbit. The moon has been applying this brake on the Earth for billions of years, and hence the days are getting longer, not shorter, they're getting longer. So we think that the Earth's rotation period back when the moon was made was something like about 6 hours. And ever since then, for billions of years, the moon has been applying a brake on the Earth, and the day is now about 24 hours. If there was only the sun at play, that 6-hour rotation would probably be stretched out to about maybe 8 hours. But what's a consequence of having shorter days? Well, rapid planetary rotation might mean high winds. If we look at Jupiter, for instance, Jupiter has got very strong winds in its cloud belts. It has a 10-hour rotation period, very strong Coriolis forces. These are the ones responsible for making typhoons and hurricanes here on Earth. And on Jupiter, the winds can be up to 500 kilometers an hour. But just because you have fast rotation, that doesn't mean you'll end up with similar wind speeds on a fast rotating Earth. One of the reasons Jupiter has got such high wind speeds is because it has a very strong internal heat source, which the Earth lacks, and so we wouldn't expect to get quite the same high speeds on Earth as we do on Jupiter, despite the fast rotation speed. Other statements I've seen on the web: without the moon, there would be no humans. I'm not sure quite how you come to that conclusion, and it's very difficult to say, well, if you reset the evolutionary clock, would you still end up with Homo sapiens, etc.? Maybe we'd end up with similar, but we wouldn't end up with the same thing. But the other statement that I definitely disagree with is without the moon, life would not have started in the first place. I think that is just plain wrong. That is just codswallop. Let's have a think about how the moon affects the emergence of life. The effect of moon on emergence of life is based on two assumptions. One is that life needs a healthy ocean. Life started in the oceans and then came out of the ocean onto land, and we need to have a certain amount of mixing of ocean layers, which I'll explain in just a moment. That's probably true. It's also said that life needs tidal pools in order to ease the transition from the ocean to the land. This was about 500 million years ago, or thereabouts. That's probably true as well, or at least it helps. Let's have a look at the first point first. Life needs a healthy ocean, and oceans need to be mixed. I'm not sure how well the colors show up, but in the Earth today, we have an ocean circulation system called the thermohaline circulation. There are circulation currents at various depths, some shallow, some very deep. And we need to have a mixture of oceans because if you didn't mix the oceans at different depths, nutrients would sink to the bottom and stay there, and dissolved oxygen would basically be in the top layers and stay there. We want the nutrients and the oxygen to be mixed because life needs both of those things, and we can't have them segregated. So we need vertical mixing of the ocean. It's very difficult to see, but perhaps you might notice that there is vertical mixing because, for instance, when deep currents come along the deep ocean bed, they hit things like, for instance, the mid-ocean ridge, which is thousands of meters high, and when it hits that mid-ocean ridge, it pushes deep currents up towards the surface. So ocean mixing does take place as long as you have some circulation of the oceans. So the question is, without a moon, would we still have these same circulations around the Earth? They wouldn't, of course, be identical because we wouldn't necessarily have the same continents in the same places. But the thermohaline circulation is driven by a number of different factors. The most important factor is variations in temperature and variations in density due to saltiness. Hence, thermo because of the temperature and haline because of the saltiness, which is the result of dissolving rocks into the water. That's the main factor that determines the circulation. There's also other factors which also encourage circulation of the oceans, one of which is surface winds, and another of which is tides. So tides is only a minor player in the ocean circulation. And remember that we don't get rid of tides by getting rid of the moon, we just change them from lunar tides to solar tides. Even with smaller solar-only tides, there would be potentially, maybe, higher surface winds, and so maybe they would compensate, and so we would still end up with healthy ocean mixing, even without a moon. What about this idea that we need tidal pools in order for life to come out of the ocean onto land? Well, it probably was an important element in the evolution of life 500 million years ago when we first got the transition from ocean to land. And indeed, the ever-changing environment in tidal pools, which are continually wet and dry as the tide comes in and out, that would lead to an acceleration of evolutionary specialization. But to say that we need tidal pools isn't quite right, because we could still get from the ocean to the land via other means. In other words, you would still have the option of transitioning from the ocean to the land via rivers, via marshes, via swamps, etc. So tidal pools might help a little bit, but they are not necessary for the transition to land. Okay, we've looked at tides. The second aspect is the axial tilt of the Earth. Statements that I've seen: without the moon, there would be no seasons. Wrong. Without the moon, the poles of the Earth would swing too far every 5 to 10 years. Also wrong. This, again, is total hogwash. Over hundreds of millions of years, we're picking that time scale because that's the sort of time scale we would like to have some stability. It's the time scale on which that life transitioned from ocean to land, many hundreds of millions of years. The axial tilt, which is often called the obliquity of the Earth has varied over a relatively narrow range from about 22 to 24 and a bit degrees. In other words, if we think of that as there's the tilt of the Earth, that's 22 degrees, and we can think of the change. Well, you can hardly notice the difference between 22 and 24, 22 and 24. So relatively small changes to the tilt of the Earth, and that has kept the seasons very stable. The moon has a stabilizing influence. It's effectively an anchor to the spin of the Earth. Because of the way angular momentum works, you can't easily change the spin of the Earth when you've got a moon relatively close by. So it anchors the tilt at a value of the current value of about 23.5 degrees, give or take a degree. But the question is, without a moon, what could happen to the tilt of the Earth? Just like a gyroscope, as soon as you take away stabilizing influences, you're then subject to small tugs of the Sun or tugs of Jupiter, and in principle, the tilt of the Earth could change. In principle, it could swing between any value from 0 degrees to 90 degrees. 0 degrees when the poles are like that, and 90 degrees when one pole would be effectively pointing in the plane of the Earth's orbit, so it could at some point during the year be pointing directly at the Sun and the other pole pointing directly away from the Sun. So that is a very extreme situation, and that is why some people say if you take away the moon, you allow the tilt of the Earth to do that, that would play havoc with the seasons, and it would be impossible for life to evolve when you had that sort of variation. You might say, just as an aside, well, does that actually happen for any other planet in the solar system? Because Earth is effectively unique in the sense that it has a very large moon relative to its size. So what do we know about the tilts of other planets in the solar system? Here's an animation where everything is done to the same time scale, so it doesn't look like Mercury and Venus are rotating. They're just rotating rather slowly. Mercury and Venus, very slow rotation, but the tilts are actually stabilized by tidal effects. The solar tides, regardless of the fact they haven't got moons, the solar tides actually stabilize the spins of those two planets. What about Mars? Mars tilt very similar to our own at the moment. But yes, it is thought that the 25-degree tilt of Mars probably has varied according to our understanding of the rovers that are now looking at the Mars climate, for instance. It does look like the tilt of Mars has changed, possibly because of the influence of Jupiter. Its orbit is closer to the orbit of Jupiter, and that has destabilized the tilt of Mars and given it a lot of variation of the seasons over millions of years. What about the outer solar system? There we have a number of planets, Jupiter and Saturn, of course, rotating quite quickly, much faster than the Earth. Jupiter and Saturn have relatively stable tilts, partly because of their mass, and it's a gyroscopic effect. The bigger the mass, the more stable the rotation, and the fact that they have relatively fast spin there, a day of 10 hours. So Jupiter and Saturn are stable because they're big and they spin quickly. It's thought that the ice giants, Uranus and Neptune, they are probably unstable at least over billions of years. It's not clear whether they are necessarily unstable over hundreds of millions of years. This is a statement I've seen so many times. Without the moon, there would be no life because of this idea of the effect on the tilt of the Earth. Again, this is just piffle. Let's have a think about the possibilities. A large axial tilt would mean extreme seasons. That is a correct statement. Yes, if you have a tilt that's significantly different from 23 degrees, it could sometimes point at the Sun and sometimes point away from the Sun, you would expect extreme seasons. But saying that that would make the Earth uninhabitable is just wrong. And we're not even arguing about hospitable here. Here they're saying it would be uninhabitable, not possible for life, rather than simply not conducive for life. There have been a number of simulations over the last 10, 20, 30 years of what would be the stability of Earth-like planets. So we're talking about a planet similar to the Earth, meaning similar mass, similar distance from its sun, similar land, water content, etc. But what would happen if we simulated an Earth-like planet at very high tilts, in other words, very high obliquity? This particular simulation found that, contrary to what you might believe, the global temperature didn't change that much from what we're experiencing now. The global annual mean temperature is 14 degrees, which doesn't sound so bad. But rather importantly, you might expect that with high obliquity, if one of the poles is sometimes pointing towards the sun and sometimes pointing away from the sun, wouldn't you get a huge buildup of ice at the poles? Well, actually, they found that there was no net accumulation of snow or ice when you went to obliquity significantly higher than the Earth's tilt of 23. So yes, you would get winters with a lot of ice, but it would melt the next summer. And they found no evidence for a runaway greenhouse effect or the snowball Earth scenarios that we have had in our past. So high obliquity doesn't necessarily mean you end up with a planet which is uninhabitable or even inhospitable. They concluded in this paper, most real Earth-like planets should be hospitable to life at high obliquity. Which is interesting because it sort of goes against what you think might be the situation. There's the conclusion. High obliquity is not inhospitable to life. Not only that, but there have been simulations of a moonless Earth in which they've basically tried to work out what are the perturbations you would expect from the pull of the sun or the pull of Jupiter or any other effects in the solar system. They found that the obliquity actually remains in the range 20 to 25 degrees over time periods of hundreds of millions of years. Remember, this is the sort of time period we're interested in because that's the time period in which life would evolve on land. So even though in principle, if you take away the moon, the tilt of the Earth might go between 0 and 90, when you run simulations, you find that it doesn't. It spends most of its time where you would expect it to be, around about where it is now. So not only do you not have a problem with high obliquity, it's actually not particularly likely to happen. It also helps if the Earth is rotating fast, which again would happen with a moonless Earth. The rotation period would be perhaps 6 hours to start with, and eventually the sun would slow it down to maybe 8 hours. But with a fast rotating Earth without a moon, well, the conclusion, a large moon does not seem to be needed to stabilize the tilt, to stabilize the obliquity of an Earth-like planet on timescales relevant to the development of advanced life. So over 500 million years or so, the lack of a moon doesn't stop life developing. Interesting couple of simulations. We do know that astronomical factors affect Earth's climate, so-called Milankovitch cycles. The orbital eccentricity as the Earth orbits the Sun, the ellipse of the Earth orbiting the Sun, changes and stretches over time periods of order 100,000 years or so. So this so-called orbital eccentricity varies, and hence the distance from the Earth to the Sun varies, and that changes how much radiation we get from the sun, and hence the Earth's mean temperature. We've just been looking at axial tilt. At the moment, the axial tilt varies, not by much, but it varies over 41,000 years or so. And presumably, if the tilt of the Earth was slightly different, then that particular cycle would also be different. And finally, there's a precession effect, the sort you see when you run a gyroscope and it spins around. Then axial precession are currently 26,000 years. For a given tilt, the pole of the Earth points to different parts of the sky. Again, with a different tilt, perhaps that particular number would change slightly, but you would always have these three different factors: change to the Earth's orbit, change of tilt, and the precession of the tilt, which part of space the tilt is pointing towards. And we now know that these three cycles combined have triggered ice ages in the past, and presumably would continue to do so even with a different tilt of the Earth. Without a moon, well, ice ages might be more severe, but not necessarily unsurvivable. I mean, let's face it, the Neanderthals survived multiple ice ages. They adapted to the cold. Ice ages don't come on instantly, you have time to adapt. You could argue, did they see the ice ages coming? Well, it depends. If they had access to laptops, perhaps they found ways of predicting climate change. But perhaps that's a little bit speculative. I would argue that if Neanderthals did have access to laptops and iPhones, they wouldn't be running climate models. They would probably just be taking selfies. So what about the magnetic field of the Earth? Again, I've seen lots of statements that take a little bit of believing. Without the moon, we wouldn't have a magnetic field. I don't think that's correct. The one that I found most astonishing is the Earth's core may have stopped turning and could go into reverse, which sounds like a Hollywood movie to me. If any of you have seen The Core with Aaron Eckhart, Hilary Swank, etc., the core stopped rotating, so they had to drill down to the core of the Earth with nuclear bombs. Of course, nukes are always the solution. You go with nukes and you restart the Earth's core. So this is clearly wrong, and these headlines of Earth's core has just started spinning backwards. I don't know quite where people get this stuff. I think I know where the origin of the misconception is, but clearly this is all absolute poppycock. Right. The Earth generates a magnetic field because it has an iron-nickel core, and that provides us with a protective magnetic field. It protects us mainly from radiation from the sun, particles from the sun which are continually streaming off in a so-called solar wind, and occasionally the sun produces a so-called coronal mass ejection, where a large amount of plasma and associated particles are thrown off, and some of them come in the Earth's direction. I'm going to show you a little CGI, a little computer-generated imagery, an animation that shows how we think the Earth's magnetic field deflected solar radiation during a geomagnetic storm in May 2024. In other words, readings were taken of this storm, and then they tried to reconstruct what the magnetic field was doing to explain the data. And just as an aside, there are some fantastic videos which are available from NASA. They have a scientific visualization studio at Goddard Space Flight Center. They have thousands of very high quality videos which are well worth browsing if anybody likes the idea of videos like the one I'm going to show you. So this is what we thought was happening during the geomagnetic storm of 2024. There's the invisible magnetic field lines of the Earth, and the sun is producing a whole load of plasma and particles which are impinging on the magnetic field of the Earth. And the green colors here show you where you have distinct distortions of the Earth's magnetic field, which is trying to deflect all of the particles that are coming from the sun. And you can get an idea of just how the storm from the sun is pummeling the Earth's magnetic field, which is still trying to protect us. Most of the particles are being deflected by the Earth's field, but when the sun is very active, the Earth's field almost struggles to keep us protected from radiation. That simple cartoon in the top right there doesn't tell us how the Earth's core actually generates a magnetic field. For that, we need to look inside the Earth to understand what's actually going on. So let's split the Earth open so we can see what's going on inside there. In addition to the crust and the mantle, what's interesting for us is what's going on in the core. There is an outer core which is liquid. It's at about 4,000 Kelvin or so, and a solid inner core at 5,000 Kelvin. It might seem a bit odd that the inner core is actually hotter and yet still solid. That's simply because it's a higher pressure being at the center of the Earth. So a solid inner core and a liquid outer core. And it's the liquid outer core that is the geodynamo. It's not the solid core. It's not the solid lump of iron in the middle. You might think of it as a little bar magnet, but that's not what's going on. It's not the solid core that's responsible for the geodynamo. It's the liquid outer core. Heat from the inner core is keeping liquid swirling in a turbulent way in the outer core. It's a very complex motion, and basically whenever you get liquid metal, in this case iron or nickel iron, whenever you get liquid metal in motion, it generates electric and magnetic fields. And that's what's happening in the core. Where does the inner core get its heat from? Well, most of it is primordial in that there are decay of radioactive atoms that have been there for billions of years. Potassium, thorium, and uranium are responsible for a lot of the radioactive decay in the core of the Earth, keeping things warm. But also, some heat is being released because the core is very slowly freezing. The outer core, which is liquid, is slowly turning from liquid to solid. In other words, the solid inner core is actually growing. It's growing fairly slowly, 1 millimeter per year. That sounds fairly slow until you think about what's going to happen over billions of years. So the Earth is not static and the Earth is not unchanging. What's going on in the inner core of the Earth is very much a function of time. There are two possible consequences of saying, right, that's fair enough, the Earth has a magnetic field, but what are the consequences of having no moon? In what ways could having no moon weaken the magnetic field of the Earth? In what ways could it possibly make the Earth less hospitable to life? There are two factors that could come into play. One is the question, did Theia, when it hit the Earth, add some iron to the Earth's core? In which case the Earth's core is bigger than it would have been if Theia didn't hit, and that would have made the geodynamo stronger. So that's one possibility. The other question is, does the moon strengthen the geodynamo? Remember, the magnetic field is not coming from the inner core, it's coming from the liquid outer core. Does the moon strengthen the dynamo by basically tidal action? We know tides affect the water on the surface of the Earth. Does the tide actually affect the liquid outer core, and does that help generate a magnetic field? So without the moon, we would not have that extra factor. Let's deal with the first point first. Did Theia add iron to the Earth's core? We're not absolutely sure, but we think Theia had a mass of around about 10% of the Earth. And if it was made at the same distance from the sun, if it was made at one of these Lagrange points, it was made in the early solar system at the same sort of distance from the sun as the Earth was, so it probably has the same composition. All the planets in the solar system have different compositions because they're all at different distances from the sun. If Theia was the same distance from the sun as Earth, presumably it had a similar composition. If Theia did add iron to the Earth's core, because Theia had a core as well, that might make the Earth perhaps a core 10% larger by adding Theia's. So without Theia, the Earth's core would now be about 10% smaller. The current strength of the Earth's field is about 50 microtesla. Don't worry about the units if you're not a physicist. All that matters is the current strength of the Earth's field is about 50. It varies over the Earth's surface. 50 is simply an average. If the Earth's core was 10% smaller, if Theia didn't add to the core, it's not quite linear. So with a core that's 10% smaller, the magnetic field would be about 15% less. So for a moonless Earth, the magnetic field strength of the surface would be about 40 microteslas. The question is that good enough to protect us? We know that the current strength of the Earth's field protects us from the sun. If it dropped by that amount, would it still protect us? It's difficult to tell, but you can run simulations again. A simulation has been carried out fairly recently, a couple of years ago, in which they tried to calculate the Earth's habitability. In other words, how does the strength of the magnetic field protect us from so-called space weather? In other words, eruptions from the sun, plasma and particles from the sun. And they did this over billions of years. They found that a magnetic field of about 5 microtesla would protect the Earth when things were quiet, when the sun was well behaved, when it wasn't throwing out huge amounts of plasma and particles, 5 microtesla would be enough to protect us. But the real question is, what do we need to protect us when the sun is active and throwing out a lot of coronal mass ejections? They calculated that about 30 microtesla would be enough to protect the Earth from violent ejections from the sun, as shown by this little animation of what happened relatively recently on the surface of the sun. Remember, we're saying with a moonless Earth, it would drop from 50 down to about 40, and it is thought that there's a baseline of 30 that we would need to keep us protected. So this would indicate, rather naively, that, well, if these numbers are right, that would indicate that if Theia had missed the Earth and hadn't added to the Earth's core, the geodynamo might have been a bit weaker, but not by enough to cause significant problems for the evolution of life, if these numbers are correct. What about the other factor? Does the moon strengthen the Earth's magnetic field by basically stirring up the liquid outer core through tidal action? There's no reason in principle why the tides don't reach that far. If they can start moving water in the oceans around, in principle, they could move this liquid around as well. Some geophysicists think that lunar tides in the outer core might have helped sustain the geodynamo over many billions of years. But I don't think everybody agrees. The consensus maybe is that the convection of heat from the inner core is all that you need to keep the dynamo going, and that lunar tides make essentially no contribution. Just as a little bit of an aside, again, we can ask the question, well, what about any other planets in the solar system? Do any other planets have a magnetic field? None of these planets in the solar system have a large moon compared to the size of the host planet. But do any of them have a magnetic field? Well, when we look, we find that Mercury does. Venus doesn't. Why doesn't Venus have a magnetic field, even though it's a very similar size to the Earth and presumably a similar composition? Well, Venus doesn't have a magnetic field simply because it's not spinning fast enough. Venus spins really slowly, and we think you really do need to have spin to generate the forces, to generate the turbulence in the liquid core, to generate a magnetic field. So that's why Venus doesn't have a magnetic field. Earth, of course, does. Mars doesn't. We think Mars doesn't have a magnetic field because it's too small. It is probable that Mars did in the past have a magnetic field, but its core froze, much in the same way that the Earth's core will freeze a long time in the future. Mars is a lot smaller, and its core froze a long time ago, and hence it lost its magnetic field. And as a consequence, probably lost its atmosphere at the same time. Jupiter and Saturn, large planets, both have magnetic fields. The ice giants, Uranus and Neptune, also have magnetic fields. It's a bit of a shame, but when it comes to Pluto, Pluto is, okay, it's not a planet, but if we just regard it as another large object in the solar system, Pluto has got a very large moon called, called Charon. And then it makes sense to say, well, if that does have a large moon, then it really matters as to whether it has a magnetic field or not. And the answer is, we don't know. Because the spacecraft that went to Pluto, called New Horizons, didn't have a magnetometer on board. They had to decide which experiments are on board, which experiments are. It's always a question of how much mass do we have? Can we save a few kilograms here or a few kilograms there? It was decided that the magnetometer wasn't essential. So we do not know whether Pluto has a magnetic field or not, despite having a large moon going around it. And just to confuse matters, Ganymede, one of the moons of Jupiter, also appears to have a magnetic field. As far as we know, it's the only moon in the solar system that has its own magnetic field, rather than effectively borrowing the magnetic field off its host planet. What about asteroid impacts? It is said that the far side of the moon has a whole load of craters made by asteroids heading in the direction of Earth that get pulled into the moon by its gravity, and hence the moon shields the Earth. Wrong. That is twaddle. You can see I'm rapidly running out of adjectives to give to these various things whilst keeping it reasonably polite. Yes, the near side and the far side of the moon are very different, and you could say that the far side appears to be very heavily cratered, which gives the impression that it's sort of been pummeled from the outside of its orbit and has clearly protected the Earth from asteroid impact. Well, that's one way of interpreting what it is we're looking at. Yes, there are more craters. Does that necessarily mean it's acted as a shield to protect the Earth over billions of years? Well, if you think in terms of geometry and just think of it as an object, a target of a particular size, the moon might look quite large when you see it rising on the horizon, but actually it's only a tiny fraction of the sky. The moon's area in the sky is only about 5 parts per million. So if you assume that asteroids can come from almost anywhere, that's not quite true, but it's good enough to start with. If asteroids can come from all directions, you would only expect a tiny fraction of them to be blocked by the moon. And remember that the moon only has a mass of 1% of the mass of the Earth, and so its gravity is not strong enough to deflect any asteroids on their way to Earth and hence act as a deterrent or a shield. The difference in the crater density is not because more asteroids hit on the far side, it's because the history of the near side and the far side are different. The near side has been resurfaced much more recently than the far side. These dark areas, these so-called seas or mare, these are lava flood plains, and basically they have covered any old craters, making them essentially invisible. So we can still see all the craters on the far side. A lot of the craters on the near side have been flooded and hence are now invisible. Why is it that there's more flooded mare on the near side than the far side? That is still an open question, and people are studying the moon to try and understand why the near side and the far side are so very different. But as far as we can tell, the moon has not acted as a shield against asteroid impact. The fifth factor that I said would make a difference, well, eclipses. We know there would be a difference. We saw an eclipse, not a total eclipse. We saw a partial eclipse quite recently. Some lucky people were on the path of totality. And of course, we have this situation that at the moment, the moon is just about the right size to cover the sun. If you wait long enough, remember the moon is applying a brake on the Earth, slowing the Earth down and sending the moon into a higher orbit. The moon is moving away from the Earth very slowly, a few centimeters per year perhaps. And therefore, eventually, the moon is going to be too small to cover the sun. But for the moment, we have this wonderful experience, the wonderful possibility of seeing a total eclipse of the sun, which of course we would not be able to see if we had no moon. The other obvious one is we would never get an eclipse of the moon. If there's no moon, of course we can't see an eclipse of the moon. An eclipse of the moon is the only time we can see the Earth's shadow directly. Okay, we're standing in the Earth's shadow every night, but in terms of seeing a circular shadow, as the moon goes through the Earth's shadow, if we take a whole series of images, we can then reconstruct, there's the Earth's shadow, and the Earth's shadow is always circular. Regardless of the geometry, regardless of the time of day, lunar eclipses always show that the Earth's shadow is circular. And so that, if you like, is proof that the Earth isn't flat. So if you didn't have a moon, you wouldn't see that shadow. Maybe one of the consequences of having no moon is that there would be more flat earthers, because we would not be able to make the argument, how else can you explain the fact that the Earth's shadow is always circular? You can only get a circular shadow from a spherical object if you illuminate it from any conceivable angle. And by the way, in case you're wondering, that simply means astronomy picture of the day. 20th of August 2008. NASA have an astronomy picture of the day, which is always worth a glance. Make it your go-to page, if you wish, on your web browser. Let's just think of a few bits of trivia before we finish. I've dealt with the serious aspects of tides and the tilt of the Earth and the magnetic field of the Earth, but we're overlooking a few other aspects of how would things be different if we didn't have a moon. And one of them that you can very easily overlook is that without a moon, there would be no Mondays. Now, maybe that's a good thing. We would go straight from Sunday to Tuesday. Maybe people don't like Mondays, but basically, yeah, we could go straight there. But of course, it also means we'd have no months. Our calendar is based on the idea of how long it takes the Earth to turn and how long it takes the Earth to go around the sun. And months is, of course, a concept based on how long it takes the moon to go around the Earth. So without months, what would our calendar look like? If the 6-hour rotation period of the Earth got slowed down by the sun, and it was probable that it would slow it down to about 8 hours or so, the moon going around the sun wouldn't change on the impact of Theia. It would still take what we now call 365 days. But if the days were much shorter, only a third of the current day, then instead of having 300 and something days in a year, with 8-hour days, there would be about 1,000 days in a year. So what would our calendars look like? If we still evolved with 10 fingers, would we end up with a calendar which is based on 10 seasons, each of which is 10 blocks of 10 days? That might be a very logical way of decimalizing the calendar. Who knows whether or not that's what we would actually decide? Of course, there's no guarantee we would necessarily end up with 10 figures if we ran evolution again. But there are other factors. Without a moon, well, how else would things be different? Well, there'd be no werewolves for a start. And my life would be slightly different in terms of giving outreach talks, because without a moon, there would be no moon landing conspiracies to argue against. And I think we would end up, perhaps, on a planet Earth that was absolutely full of very confused sea turtles, because they rely on having the moon telling them if they come out of the sand where they're hatched, the moon effectively, and the reflection of the moon on the water tells them where the sea is to make sure that they can then go into the safety of the sea. So quite what sea turtles would do without a moon, I don't know. We have a few minutes spare, so let me just say, not how would the Earth be different in terms of what if we had no moon, but what difference would it make if Theia hit Venus instead of hitting the Earth? How might it have influenced the way we perceive the universe? This is based on the premise that let's assume that life still develops the same way. It's a big assumption. Let's assume that because we don't have a moon, life would still develop the same way. And for the sake of argument, let's assume human civilization still came and went in much the same way. How would it affect the way we perceive the universe? This is not any original thought of mine. This is based on Isaac Asimov, who wrote an article back in 1972 in the magazine of fantasy and science fiction. I read it sometime in the 1970s, I can't remember exactly when, and I thought, yeah, this guy has got quite an imagination. So, what difference does it make? Venus has a size and a mass and a composition very similar to the Earth. It was made a little bit closer to the sun, but it's still a rocky planet with a mass that's very similar, and we think a composition that's very similar. So if Theia had hit Venus rather than had hit Earth, then you can argue that if it hit at the same speed, etc., it would have generated a moon much like our own moon. So I'm just using lowercase m for moon to mean a moon of Venus, and capital M to be our moon. So the impact of Theia may have produced a moon similar to our own. Assuming life on this moonless Earth had evolved into humans and everything else stayed the same, what would we have seen of this Venusian moon? And we can calculate, given that we know what the moon is like now and how bright it is, we can calculate if we took that moon and moved it to Venus, how bright would it be? And it turns out it would be as bright as one of the brightest stars in our sky. And Venus is exceptionally bright, but it would be possible to see the moon of Venus. It would be like a bright star, and it would go back and forward. If it's made in the same way and it goes round in the same time, it would take a month to go round Venus, and the distance between this bright dot and Venus would be about 10 to 20 arc minutes. Relatively small angle in the sky, but bear in mind that human visual acuity is about 1 arc minute. That's the smallest thing you can resolve. So the distance between this point of light and Venus is easily resolvable to the naked eye. You would be able to see a moon of Venus with the naked eye. Perhaps that would mean that astronomers from some ancient civilizations, such as, for instance, the Sumerians or the Babylonians, who are both interested in astronomy, they would have observed this point of light. They would see Venus moving through the night sky, and as it moved through the night sky, they would see this small point of light apparently going backwards and forwards. They wouldn't necessarily be able to work out which way it was going, but they would be able to see that this point of light always follows Venus and appears to be moving around Venus. You can believe that they would conclude that some objects in the sky do not rotate around the Earth. They rotate around other objects. There appears to be a companion to Venus. So the idea of a geocentric model where everything revolves around the Earth, that eventually got replaced for us by the heliocentric model, where we realized that everything goes around the sun except for the moon that goes around the Earth. For us, it was the invention of the telescope that led to that. The telescope, Galileo pointed his telescope at Jupiter, and we saw moons going around Jupiter in much the same way that the Babylonians could have seen a moon going around Venus. And it's us seeing moons going around Jupiter that told us not everything goes around the Earth. So the change from the geocentric to the heliocentric model of the solar system for us happened in the 1600s, and that change from geo to heliocentric catalyzed the scientific revolution and the age of reason, or the Enlightenment, if you like, in the late 1600s. So you could say, if Venus had a moon that was visible to the naked eye, perhaps this fundamental paradigm shift in human thought in the 1600s, the change to the way we thought about our place in the universe, might have been kickstarted thousands of years earlier. Not in the 1600s, but perhaps 2000 BC. It would have taken technology a bit of time to catch up, but we're talking about a change in the way we think about the universe. Asimov never actually said or speculated if the age of reason actually kicked in 2000 BC, where would we be now? But it's an interesting thought. So let me summarize. In terms of tides, we can ask, would a missing moon mean no life? No. In terms of the axial tilt changing the seasons, would a missing moon make the Earth inhospitable to life? No. In terms of a magnetic field, would a missing moon make the magnetic field too weak to protect us from explosive emission from the sun? No. In terms of asteroid impact, would a missing moon make Earth more of a target for asteroids or anything else floating around the solar system? No. In terms of eclipses, would a missing moon mean no eclipses? Well, yes, it would, which is a bit of a shame, but that doesn't have a direct impact on the evolution of life. Some people believe in the so-called rare earth hypothesis, the idea that life, the development of life, the evolution of life, and in particular complex life, needs a large moon for the reasons we've gone through, the idea of tides, the idea of axial tilt and seasons, etc. The rare earth hypothesis says you need a large moon, and therefore, because large moons are not very common, the Earth could be unique in the galaxy, and this is the only place we have life. In other words, we are alone. I would argue that a missing moon does not mean no life. Earth is not unique. There are billions of Earth-like planets in the galaxy, so even if a lot of them don't have a big moon, that doesn't matter. Life can still evolve, and a very small fraction of a very big number could still be a very large number of civilizations out in the galaxy. I agree with Carl Sagan. The cosmos teems with complex life. So if Theia missed the Earth, would we miss the moon? In terms of the evolution of life, I would argue no. But if we humans ever evolved with a missing moon, well, it just wouldn't be the same without it. Thank you very much.